Welcome to Lab 3 titled Magnetic Field of a Bar Magnet. In this lab, we will investigate the distance dependence of the magnetic field of the small bar magnet, measure the magnetic field of the magnet on-axis and off-axis, and create a computation model that compares the measured magnetic field to the computed magnetic field. We found that as the magnitude of the net magnetic field increased, the distance decreased, and the magnetic dipole moment was 1.54 Newton meters over Tesla. The measured off-axis field is 3.81 times 10 to the negative 5 Tesla, and the computed off-axis field is 2.46 times 10 to the negative 5 Tesla. The Biot-Savart law is a formula that relates the magnetic field produced by an object at the observation point to the current running through the object and the distance between the source of the field and observation point, and that is U naught over 4 pi times QV crossed with R hat over R squared. When R, the position vector, is greater than the radius through the center of the loop, the magnitude of the magnetic field of a loop has the shape of the on-axis magnetic field of the dipole, as shown between these two equations, which are almost practically similar. The magnetic dipole moment is represented by I, the current, times the pi r squared, and the direction of the on-axis magnetic field is the same direction as the magnetic dipole moment and the same direction as the conventional current I. Here we see the equation for the magnetic field of the magnetic dipole on the perp axis, in which the magnitude is half the value of the magnetic field of the magnetic dipole on axis, and the direction of the perp axis is opposite the magnetic dipole moment. We also have the equation for the magnetic field due to the bar magnet, which is the magnetic dipole, and we also have the general equation for the magnetic field of the magnetic dipole, which is calculated through multiple variations and used in the experiment. Here's a free body diagram of the magnet, in which the system is the observation point or the magnetometer, and the surrounding is the bar magnet, which produces the magnetic field. The key subjects for this lab is that we will determine the magnetic field of a bar magnet by treating the bar magnet as a magnetic dipole. Here's a quick run through for the lab. We'll first compensate for the Earth magnetic north by positioning the magnetometer app to read close to 0 for the x-axis, and then we'll find the magnetometer chip on our phones. We'll then calculate the on-axis magnetic field and measure the off-axis magnetic field by using a similar procedure in which we measure the distance based on certain levels of the B field. Based on our experiment, we see that the magnetometer reads a value of almost 0 as the device moves away from the magnet, and there is an increase in the measured x component of the magnetic field as the magnetometer moves closer to the magnet. Here are the results for the lab experiment. Note the line of regression and the decreasing distance between the magnet and the observation point as the magnetic field increases. The off-axis measurements are shown on the bottom of the page. To solve for the magnetic dipole of the bar magnet, we can use the regression line for the data and construct the distance dependence from the experimental data using the logarithmic equation shown below. From this, we can then determine the value of n, which is the slope of the regression line, and k, which is the y-intercept equals ln(k), and get those two values, or constants. Now we can then set the two equations we have for the magnetic dipole for the magnetic field equal to each other, and plug in our known constants to solve for the magnetic dipole moment. And once we do that and rearrange the equation as shown below, we get that U naught, or the magnetic dipole, is equal to 1.5495 Newton meters over Tesla. Here's the first part of the code that accounts for the magnetic constant, the magnetic dimensions, and calls for the magnetic magnitude. Take note of the general equation for the B field off-axis for the magnetic field shown below, which the code goes through each line and calculates the represented equation. Starting in Log 57, we see the calculations for the on-axis B field equation and the perpendicular axis B field equation being done here. Below that, we see the code for the creating the arrows for the magnetic field on the on-axis and perpendicular axis. And then in the second part here, we see the average D perpendicular form from the equation, and this is D. Lastly, we see the code presenting the results for the B field at distance D. Here are the results from the line of code. Note the resemblance to the free body diagram a few slides back. Here's the discussion for the lab. As the distance between the observation point and the bar magnetic decreases, the magnitude of the magnetic field increases. The magnetic dipole moment was 1.5495 Newton meters over Tesla, and the experimental vector magnitude for the magnetic field off-axis was 3.811 times 10 to the negative 5 Tesla, while the computational vector magnitude for the magnetic field off-axis was 2.46 times 10 to the negative 5 Tesla. From this, we see that the net magnetic field magnitude for the experimental model is larger than the computational model and differs by a factor from 1.34 times 10 to the negative 5 Tesla. We see that the computational model does not take into account any magnetic field in the z direction, which could be one of the reasons. Possible errors in the lab is other sources of magnetic field distorting the measurements, which could be done by including those magnetic fields in the calculations or going to a separate location that doesn't have any magnetic field at all. Inconsistent placement of a phone, which can be solved by keeping the phone as stable as possible. Error due to rounding calculations, which can be solved by keeping calculations as is throughout the experiment. And a measurement error with the magnetometer, which can be utilized or fixed by getting a different software substitute program. Due to no compensation for the magnetic north and us laying out the meter stick at some intermediate angle with respect to Earth's magnetic field, the measured magnetic field will be different because the magnetic north of the Earth will no longer be accounted for in the measurement, resulting in the contribution of the magnetic field to the x-component of the magnetic field. The net magnetic field value will differ from the computational model value by an even greater amount due to the significant change in the x-component and change in the y-component, and because we laid a magnetometer on the flat surface, the z-component will not change. If I were to stick two identical magnets together end to end and run the experiment again, there would be an increase in the magnitude of the magnetic field due to the combined magnetic fields from the two magnets. Due to the law of superposition, we could expect the magnitude of the new magnetic field to be approximately double the magnetic field of a single magnet, and the measured distance for each magnetic field will decrease due to the increased magnetic field magnitude from the two magnets.